All right, let's take a look at section 5.5, which is continuing on with derivatives and integrals of various exponentials and log functions. This is basically considering the situation where the base is not e. All right, so let's start off here with number one. The derivative of a to the x, where a is not e, although this rule does work if a is e. But here's how this works. It's equal to ln of a times a to the x. And let me just take a second to prove that to you. I'll do that over here. I'll erase this in a second, but let's look at a to the x as our function. Let's set up an equation. Let's say y equals a to the x. So what I'm going to do is I'm going to differentiate, or excuse me, before I differentiate, I'm going to take the ln of both sides. And so ln of y equals ln of a to the x. If you use your log rules, you can bring the x down in front, like so. And now we're going to differentiate with respect to x, so we want to find dy dx. It's going to be a little implicit differentiation. So it's going to be 1 over y times dy dx is equal to ln of a. Therefore, dy dx is equal to y times ln of a. And we already know from our first step that y is equal to a to the x, so dy dx equals a to the x times ln of a. And of course, dy dx is the derivative of a to the x. That's the derivative of our function there. You get a to the x times ln of a. So same thing we saw up there. Just a quick little deal there. Not anything you have to remember how to do, but just a way of proving it just to see that it actually is correct. Okay. And then, of course, if we're talking about a composite function, a to the u, that's simply a chain rule. So this would be ln of a times a to the u times u prime, or you could say ln of a times a to the u times du dx. Of course, same thing, just using Leibniz's notation instead of Newton's. Okay, so moving on to number 2, the derivative of log base a of x. This is 1 over x ln a. And I'll prove this to you as well. Just use this space down here. And I'll erase it in a minute. So let's do the similar process. Go y equals log base a of x. But instead of taking the ln of both sides or something like that, let's change the base to ln. So maybe you remember that change the base formula. Log base a of x is equal to ln of x over ln of a. Now let's differentiate both sides. So dy dx is equal to, of course, the derivative of ln of x is 1 over x times 1 over ln of a. And that's 1 over x times ln of a, like so. So again, hopefully that's maybe proved that to you. Just a quick little proof on how that works. Okay, and of course, if you have the composite side of things, you just have to multiply by the derivative. What's on the inside? Just the chain rule. So 1 over x ln of a, 1 over u ln of a times u prime. So a lot of times you'll see that as u prime over u ln of a. Another way you certainly could say that. Okay, and then finally number 3. This is where we integrate where there's an exponential that's not having a base of e. So this is equal to 1 over ln of a times a to the x, and then of course plus c. I'll prove this one to you as well. It's a little bit simpler. The integral of a to the x dx. This should fit the pattern for exponentials, and if you think about it, the integral of ln of a times a to the x would just be a to the x. So what's going on here is this is one of those scenarios where you could use u substitution, or in this case, let's just do where we messed up the chain rule. So in order for this to work, we need an ln of a inside there. So we need to multiply the outside by 1 over ln of a. So then when we integrate, the 1 over ln of a is still there. The integral of the integrand here is just a to the x, and then of course you've got the plus c. So just a little thought process there on how that works. Okay, so let's take a look at some examples. Number 1, We're supposed to differentiate. It says y equals 2 to the x. So again, this is very patterned. It's a little more of just kind of a skill set, memorizing patterns and applying them. So the derivative of y equals 2 to the x would be y prime equals ln of 2 times 2 to the x. The way that I tend to remember this is that I know that this should work for e. So ln of e, of course, is 1. So if you thought of the 2 as an e, it would still work. You can just memorize it, of course. I'm sure we could come up with a better way to remember that if we needed to. Okay, number 2 is very, very similar, except as you know, the exponent is a different function besides x. It's composite. So y equals 2 to the 3x. Y prime would equal ln of 2 times 2 to the 3x times the derivative of what's on the inside, so it'd be times 3. A lot of rearranging that could be done there using some log rules. We can move the 3 in the front. And of course, if you got a coefficient in the front, it can move up to be the new exponent. So that would be y prime equals ln of 2 cubed times 2 to the 3x, which would be ln of 8 times 2 to the 3x. There's a lot of ways this could be written out. It does pay to be solid at your exponential and log skills in order to do well. They'll sometimes throw something at you might not expect. So it's good to be up on that stuff. We'll review as we move forward. Okay, number 3, y equals log base 4 of x. And again, I think that the idea here, the way these are easiest, is if you just have in mind the pattern, be able to recognize it and apply it. So y prime in this case would be 1 over x ln 4. All right, a few more examples, I guess. Number 4, really similar to what we just did, except we've got the cosine of x is the argument on log base 10. So y prime would equal 1 over cosine x ln of 10. So again, it's just working on that same pattern, times the derivative of what's on the inside, so that would be negative sine of x. You could write it in a number of ways. Negative sine x over cosine of x ln of 10. You could do some combining with the sine and the cosine. I'm not going to go there, but certainly you could do some awesome trig stuff with that. Okay, last example, number 5. Again, this just fits the pattern that we talked about earlier. Integral of 3 to the x. In order for this to work in your integrand, you'd have to have ln of 3. We have to multiply the outside times ln of 3, or excuse me, 1 over ln of 3. So our final answer ends up being 1 over ln of 3 times 3 to the x plus c. Okay, so that's it for examples. I think maybe you've noticed that an example in section 5.5, it's really about skills. It's about memorizing patterns. Certainly some derivation and thought process can go into that, but I think the most efficient use of your time and energy is going to just be to have these stored away. The honest truth is, on the AP test, our final exam, that kind of stuff, problems like we see in 5.5 might pop up once or twice at the most on the test. So it might be something that you decide, I'm not going to put much effort into that. But if you think about it, 1 or 2 points here or there could make the difference, especially if you've got several different 1 or 2 points. So I would try to make the most of this. And honestly, these are pretty simple as long as you have things memorized. And as long as you have it memorized and you're solid, you almost could think of these as just free points, right? Because they're not going to get that complicated. So in any case, that's it. Make sure you're practicing this stuff, and I'll see you guys in class.